Cool. So today I'm going to be talking about prompting methods, and this is a recently popular and interesting trend. I kind of like played around with it a little bit earlier in the class when I was showing the results from Bloom, etc. So as the recommended reading, we have this survey paper that we wrote last year. It's reasonably, I think, systematic, and it covers a lot of the stuff we talk about in prompting. There's a few extra things, new things that I'll try to talk about at the end of the class if we have time. But I'd suggest taking a look here if any of the things I talk about today go by quickly or other stuff. Okay, so there's kind of been four big paradigms of NLP progress in the past recent history. And I guess at the very beginning of NLP, we tended to have rule-based systems where we went in and actually specified the behavior of the system by hand. And these are still used in some industrial systems due to their how easily predictable they are. And you can go in and make things do essentially simple and predictable things. But if we're talking about machine learning based NLP, the very first kind of paradigm in machine learning based NLP was feature engineering, where we went in and specified the features that we thought would be useful for the task by hand. Then after that, when we transitioned to neural NLP, we had architecture engineering, where we tried to engineer the architecture of our models. After that, we followed with objective engineering, which was kind of the pre-training that we talked about 2 classes ago. We choose an appropriate pre-training objective. And recently, we've been seeing people moving in the direction of doing prompt engineering. And one thing I should point out is that none of these is entirely obsolete, I guess, but the relative importance of all of them has shifted over the years. So to go a little bit more into feature engineering, if we talk about feature engineering, usually we're talking about some sort of fully supervised learning, often not using neural networks, using models like, for example, support vector machines or conditional random fields. And the time period, it was most popular through 2015, where 2015 was kind of when we had the really big, exciting advances in neural models for NLP. And we would do things like manually defining features that say, okay, I want you to pay attention to this word because it's capitalized. So we'd have a feature that would say this word is capitalized or not. And then we would use that in recognizing entities. Or we'd have a feature that says, this word is at the beginning of the sentence, this word is at the end of the sentence. And we could use things like support vector machines, which learn feature combinations. Architecture engineering was generally used with fully or mostly fully supervised learning with neural networks. As I said, it's not completely obsolete at the moment, but we've transitioned away from it, and it was most popular 2013 to 2018. And the characteristics are that it relies on neural networks. We usually don't need to manually define features, so we'd let the neural network learn whether a word is capitalized or not and whether that's an important thing for the model to be knowing. But we would go in and modify the structure. So we might get an LSTM, we might have a convolutional neural network, we might have a transformer-based model, in kind of how we would get our model to learn the things that we want it to be learning would be based on this. Sometimes this was used together with pre-training of language models, but usually it was only for shallow features, such as embeddings. So this would be something like word2vec or other things like this. And then the full model parameters would be kind of learned end-to-end in a supervised fashion. An example could be something like a CNN for text classification. Now, moving to objective engineering, this is kind of still one of the most popular paradigms. And so we have it from 2017 to now, where 2017 is basically like the advent of BERT. Again, there was pre-training before that, but BERT was what really popularized it. And then we have pre-trained LMs are used as initialization to the full model, both shallow and deep features. And there's less work on architecture design. and we spend our time engineering objective functions. The reason why there's less work on architecture design is because now with the pre-training objectives like language modeling, essentially the models learn relatively good features of, whatever language they're trying to model without explicit, encouragement through designing an architecture. So we can get most of that through objective functions, and that could be like BERT plus fine tuning. And again, this is, there's a spectrum of these things, but that's kind of the general trend. And then finally, prompt engineering. I say 2019 to now because it did exist before 2019, but it really became popularized in 2019 or 2020 with, for example, GPT-3 becoming popular. And NLP tasks are modeled entirely by relying on language models and the predictions through language models. And the tasks of both shallow and deep feature extraction and prediction on data are all kind of given to that language model as tasks for it to solve. However, now if we just have a language model and we don't give the language model any bias about what task we're trying to solve whatsoever, it'll just act as a language model. And if you remember, if I didn't properly specify to the language model what I wanted it to do, I would write something like Barack Obama's job is, and then it would follow with one of the most difficult things in the world or something like that, which is not what I wanted. I wanted, president of the United States or former president of the United States and motivational speaker or, other things like that. And then representative work could be GPT-3 or a number of other things I'm going to talk about this time. And so basically, the idea of what prompting is it's encouraging a pre-trained model that was trained on a different task to make particular predictions by providing a prompt specifying the task to be done. And so, giving an example, we could take a large language model and ask it and prompt it with JDK is developed by, and then we ask it to follow up and it would output Oracle. And then we have, this is a super long text TLDR and it would output a summary of that text. Or birds can, and it would output fly and we would get, some sort of common sense knowledge. And so as you can see, in all of these cases, we're not really changing the model. The model is a general purpose like BERT model or BART model or Ernie model GPT-3. And the only way we're controlling what the model outputs is by providing it text beforehand. Any questions so far? Okay. So to make this a little bit more formal, if we talk about the general workflow of what we need to do prompting, we need to add a prompt to the text that we want to be using as an input. We want to be making a prediction of the answer using the language model's predictive probabilities. And then we want to do a mapping from the answer to the label we desire. And in some cases, some of these things are relatively trivial. In other cases, they're less trivial. Okay, so let's look at prompt addition. Basically, what it is it's given an input X, we transform it into a prompt X prime through two steps. The first thing we do is we define a template with two slots, one for the input and one for the answer, where we're calling the input X and the answer Z. And then we fill in the input slot with our actual input. And so here's an example. We have our input X, and then we have our prompt template, where our prompt template has a slot for X and Z. And after we have filled in the prompts, we can call this a filled prompt or something like this. We get X prime. And so we start out with our input, I love this movie. We have our template X, overall, it was a Z movie. And then X prime becomes, I love this movie, overall, it was a Z movie. And the idea is that we can then ask the language model to predict the Z, and that would allow us to make a prediction. For answer prediction, as I said, it's basically filling in Z. So we would ask our language model to make a prediction. Maybe the top scoring word in this position is fantastic. And so then we would have fantastic be in here. And then we have mapping. And mapping is basically given an answer, we map it into a class label. And we don't necessarily want, as a prediction from a sentiment analysis model, quote unquote, like fantastic, right? Because fantastic would be one word. We could also have good, wonderful, all these other kinds of words. So we need a way to map the language model's like answer space into the space that we actually care about, which is whether it's positive or negative. And so this is the overall workflow. And then there's lots of details about how we can do any of these things here. Are there any questions or? Okay, just go on through. So another thing I'd like to talk about is types of prompts. And there's kind of two major types of prompts. This is one example of a prompt here. Or sorry, this is a thing that we are calling a prompt. And then we have a filled prompt. And the filled prompt is where we fill in Z. We could also call an answered prompt a prompt with an appropriate answer. I'm not going to use this a whole lot, but we use it in the survey paper. And then we also have another couple types of distinctions of prompts. So we have a prefix prompt or a close prompt. And a prefix prompt is essentially a prompt where you fill in the prefix and then you ask the model to like fill in anything after that prefix. And what we're calling a closed prompt is essentially a prompt where you can have inputs on, where you can have words on either side of Z here. And either one is like more appropriate for different types of models. So if we think about a few design considerations for when we're doing prompting, the first one is which pre-trained model do we use? Usually the answer is a good one, because it needs to be a good language model in order to do well at prompting. However, still within that, there's a few considerations about which one you want to be using. Also, how do we come up with the prompt that we want to be using? How do we pick the answer that we want to be using to represent the label that we want to be predicting? And then there's a bunch of different ways we can further expand on prompting. And then finally, this is really important at the end. I think there's a very interesting connection between prompting and other training strategies. And I'm going to be talking about those as well. And this is a figure from the survey paper that we had. So first, I'd like to talk a little bit about the pre-trained model choice. We already talked a lot about pre-trained models, so I'm just going to go through this very quickly. But from the point of view of prompting, it's kind of important to have an idea of how the different models interact with different prompting strategies. And also another thing is I'm going to talk about encoder-decoder pre-training models, which I haven't talked about yet, but I think are, now is a good time to be talking about this. So left to right language models are the language models that we've been talking about from the very beginning of the class. Basically, they predict from left to right in an autoregressive fashion. If you want to go back to when they were first proposed, they were actually proposed by Markov in 1913, where the name Markov model comes from. Does anyone know what the first language model was used to do? Any ideas? Actually, no. Yeah, it's character prediction on Russian text. So that's good. I got another nice one in Zoom, which is predicting stock, which might have been a good, well, a lucrative way to make predictions. But yeah, it was next characters of Russian text for the purpose of literary analysis. So actually, the first Markov model was indeed a language model. It was a character-based language model of Russian. So we've transitioned from count-based to neural network-based ones. This is especially suitable for large-scale LMs, and we've seen a lot of them: GPT-1, 2, 3, Bloom, OPT, Palm, etc. And the role with respect to prompting methods is it was one of the earliest architectures used for prompting, and it was also usually used with prefix prompts. And they fixed the parameters of the pre-trained language models. So usually you just give a prompt in the prefix and let the model continue saying whatever it's going to say after that. Masked language models like BERT, we've also talked about a lot about them as well. With respect to prompting, these are usually combined with closed prompts. So usually we use them when we can have like a fill in the blank thing. They're often used for not for like language generation tasks, but for natural language understanding tasks. One of the most popular examples, which I'm going to talk about in a second, is predicting facts, like where somebody was born or what their job is or other things. Another example of a language model, which I haven't talked about a lot, they're not the most popular right now, but for completeness, it might be worth mentioning them. They're prefix language models, and prefix language models are basically trained with both autoregressive and bidirectional masking. So you have like the first part of the language model is trained with bidirectional masking. The latter parts of the language model are trained with autoregressive masking, so left to right masking. And these are nice because you can share the parameters of the model. You can have only a single set of parameters, but you can allow for both varieties of masking to be handled. So another thing is the prefix language models. They can use masked language modeling when training the bidirectional masked areas. And this kind of gives you the best of both worlds. It allows you to solve both close problems and left to right prediction problems. And it seems like that's a nice feature to have both of them combined together. There's a few examples of this, like Unit LM and Ernie. And as I said, these are less widely known than some of the others, but it's still worth knowing, and it connects together with what I'm going to be talking about next. I had a question in Zoom, which is, what is a difference between a close and a prefix prompt, and why is it important? So just to go back, the prefix prompt, you are limited to have Z be the final, like essentially token in your input. And the reason why this is useful is if you have a left to right language model, it's very easy to use a left to right language model on this prediction task because you just encode up to this part and then you start predicting the next word. On the other hand, a closed prompt is something where Z basically happens in the middle. So you could have words on the right. And the nice thing is that this is a little bit more flexible. You can fit, like, for example, in a prefix language model, you can only have overall this movie is blank, and you couldn't like express the fact that this is maybe a more natural framing of how you would say this in English. Yeah.
It might help to mention that the word close comes from like multiple choice questions where there's a blank in the sentence.
Yeah, and so what Bob pointed out is it might be worth saying that close comes from multiple choice questions where there's a blank in the sentence. So like also let's say you wanted to solve a multiple choice test. A lot of the multiple choice tests would be framed in this way. So really you have to use a closed prompt. You have no other easy way of doing this. Great. Okay, so prefix language models, as I said, are a little bit more esoteric, but they're a nice jumping point from the previous models to the next variety of models that I'm going to be talking about. And these are encoder-decoder pre-trained models. And the characteristics of these models are basically that they're trained using a denoising autoencoder objective. I'll give some concrete examples pretty soon. And usually they use two transformers, one encoder and one decoder, to handle the input X and the output Y separately. So you can see this in this figure because we have the light blue examples over here. from the encoder, and the orange examples over here from the decoder. And almost always, these models are trained on monolingual text by doing some sort of corruption operation to the monolingual text, to the input text, and then trying to undo that corruption operation when generating the output. And some examples include BART and T5, and these are both very widely used models. They're particularly widely used for pre-training for sequence-to-sequence tasks, so things like summarization or machine translation or other things like that. So to give some representative methods for these, we have MAS, BART, Unit LM, and T5. So MAS was kind of the first popular method for doing this sort of encoder-decoder pre-training. And the way it worked is essentially they have an input sequence, X1, X2, all the way up to X8. And they mask out some sequence or sequences in the input. And then on the output side, they predict the masked sequence. So here you can see they masked out X3, X4, X5, X6. And then they tried to predict X3, X4, X5, X6 on the output. And then on the decoder side, they mask out everything other than the things they predicted or the previous inputs. And the reason why they do this is basically they want to ensure that the output here, or that the decoder has to attend to things on the encoder side in order to pass information from the encoder to the decoder. And that's important because, like, if we're doing summarization or machine translation, we want to make sure that the model has the ability to pass information from the encoder side to the decoder side. So in order to do this, in particular, to predict the first word in the output, you really need to have a good idea of what like X1, X2, X7, X8 are encoding in order to make an accurate prediction over X3. So a contrast is BART. And BART followed shortly after MAS. And BART has been particularly successful, I think, for two reasons. One reason is that because it's a like sophisticated method. They use a lot of different corruption methods, basically. So they do things like token masking, masking out individual tokens, deleting tokens from the input, permuting sentences, document rotation. So they rotate things within a document. And they also blank out individual inputs and try to infill them. So it's not just masking individual tokens, but it's masking entire sequences of the input and trying to reproduce them. And so each of these has like different kind of functionalities. This helps you solve closed tasks or learn good representations of individual words, kind of like BERT does. This one, I guess token masking and token deletion are similar. Text infilling, this allows you to infill text. So for example, let's say we had, I will today. If you had something like BERT that was only masking out individual tokens, then BERT would only be able to predict, like, I will eat today, I will run today, I will sit today, or something like that. Whereas BART, because it masks out not just individual tokens, but it actually masks out like longer sequences as well. It could theoretically produce something like, I will go to my class today, or something like that. So it can fill in multiple sequences as well. Then the sentence permutation and document corruption ones essentially help you capture like global coherence of the inputs. I saw a couple of questions. One, two. Yeah, sure. I'm guessing you don't care about what comes after F6, right? Even with the word, do you ignore the output, or do you stop making the decoder give after? So they're used in the encoding side, so it can do bidirectional encoding from the left side and the right side, but it doesn't make those predictions. Yeah. Yeah.
Yeah. So for that,
Yeah.
I was wondering,
Yeah, BART can fill in as many tokens as you want. So one other thing I should point out is that BART always outputs the actual sentence. And this is actually important. I think this is another reason why BART is successful. A lot of the other ones aren't actually outputting the whole output token sequence or document. Like mass is only outputting the things that were masked out. Whereas BART is always reproducing the original sequence. And because it's doing that, you know, what it will do is it will basically take in a mask and it will predict a sequence of like, I will go to school today. And I think this is particularly useful for example, sequence generation tasks, because every single time the decoder is being trained, right? The decoder is being trained to generate a natural looking sequence. And so that's good if you want to do something like summarization, where you always want the output to be a natural sequence, essentially. So, yeah.
I get it. So in Word, when you say that it outputs information, do you mean that it's so for example, C will only give C, it will never give the conjugated form of the word?
Oh, in BERT? So BERT, basically you're only masking out a single token and predicting the single masked token. So whatever is masked out, it will only predict like a single token.
Well, I think I can form my question better. So when they say one single token, and usually when you see word examples, the conjugation of words gets split into multiple tokens.
Right.
So does it only create like the unconjugated form of something?
So that's a good question. And to repeat the question was, will BERT only output like the unconjugated form? Because very often the conjugated form is split into two. And the answer is yes. So if it's split into two and you're doing masking like this, there are ways, but there's no easy way to basically, you know, output conjugated form. So actually BERT is not very well. We actually have a paper called X Factor, which I won't pull up because it's not that important. But basically we were trying to do a multilingual prediction of facts, but facts could end up being multiple tokens, like he was born in the United States of America or something. We had to go through a bunch of pain in order to like get these masked language models to predict those multi-token things and compare things of different token lengths and stuff. So BERT is definitely not good for something like where you need to do a close with multiple tokens. Yeah. Yeah, the corruption's randomly applied with like different probabilities. I forget the exact probabilities here, but I have two questions on Zoom and then I'll get to this one. So one question on Zoom was, what's preventing the decoder from copying X3, X4, X5 from its own input in mass? And so basically, if you look very closely at this slide, you'll see that X3, X4, X5 are basically masked out in the input, are masked out in the input here. And so because of that, it wouldn't be able to copy them directly from the input. And then I had another question, which is why are X1 through X3 and X6 through X8 masked out in mass? And actually X1 and X2 are masked out. In a normal encoder decoder, actually what you would see is X1, X2, X3, X4, X5, X6, X7, X8. And then on the input here, you would have the start of sentence symbol. And then you would have Y1, Y2, Y3, Y4, Y5, Y6, Y7. And so basically what it's doing is it's masking out the beginning of sentence symbol. And then Y1 and Y2, which correspond to X1 and X2, which are the non-masked things here. So that's the motivation for this masking on the decoder side. Cool. I had another question. Yeah. How is text infilling different than masking plus deletion? Well, I guess probably the big thing is believe they don't do both at the same time, but I'm not 100% certain on that. But I think infilling is basically masking plus deletion. You mask out some things and you delete other ones. Yeah. Cool. Nice. Oh yeah, one more question.
I'd like to understand the extent to which sentences can be reconstructed. Like, if you provide a one-line summary, can it reconstruct something on its own knowledge?
Yeah, so the question is the extent to which sentences can be reconstructed at all. I mean, practically the answer is obviously if you corrupt the sentence enough, there's no way you can reconstruct the original input because like even the most knowledgeable and skilled of humans can't do that, right? So there's a limit. My impression is of BART or any other language models, they're better or worse at doing certain things. So like, for example, if they were doing something like correcting grammatical errors, they actually can be remarkably good at that. Like, also, I don't know exactly the model that they're using in like things like Grammarly or, you know, Google Docs or something like that, but I imagine it's a model a bit like this, and they're remarkably good nowadays, right? And however, if you start going into things like factual knowledge, models are actually not super great. Like they make lots of mistakes about, you know, who is born where or other things like this, which is not surprising because they haven't seen it a lot in their training data. So I guess it really depends on the type of problem that you're solving. Cool. Okay. So another one that is worth knowing is MBART, and MBART is basically BART trained on multilingual text. So it's trained on you know, both English and Japanese or whatever other language. Not a whole lot to say here other than the fact that it exists. There's also MT5, which is very useful. If you're thinking of doing machine translation as a target topic, I actually, there are better things, and usually I would recommend training on something that was trained with parallel data also, because there's lots of parallel data and you can just pre-train on it and you'll have a good multilingual model. And for that, one model that I've been using recently is called Delta LM. It works remarkably well. So that's one I'd suggest if you're using machine translation. Unit LM, I talked about this a little bit before. Basically, it's a kind of an encoder-decoder model, but it uses a single set of parameters that can be either you know, autoregressive, bidirectional, or a mix of both. And so this mix of both thing can also act as a stand-in for you know, an encoder-decoder model, because this essentially is an encoder, like it's essentially like a transformer-based encoder-decoder model, right? Like bidirectional masking on the input and unidirectional masking on that. And then T5 is another useful one to know about. It has a bunch of objectives. The paper here is actually pretty nice. They compare a whole bunch of different, you know, design decisions, and they explain why they set up their experiments in this way. But basically, they train using an encoder-decoder style objective, a language modeling objective, a prefix LM objective. They also do like span-based masking and other things like this. And they train on lots and lots of data. And they also have very large models. So I think one of the major draws of this is you can get an 11 billion parameter model and use it on if you want to. So you can start out with the smaller models and scale up to big models that are rather effective. And I forget exactly the size of BART, but that's a lot larger than BART. I'll just skip over that. Okay. So for prompting style methods, the application of prefix LM and encoder decoder models in prompting is very widely. They're used for conditional text generation. Usually they're fine-tuned for conditional text generation style tasks. They can also be used for generation-like tasks. So for example, information extraction, like you say something like, tell me all the entities in this sentence, and it will decode all of the entities in the sentence, or tell me all the entities in the sentence and their types, and you could decode all the entities. Question answering also similarly. Okay. Any questions about that before we move on? Okay. I'll wrap up and say I highly recommend them if you're doing summarization or machine translation or other tests like that. Cool. Okay, so the next thing that I'd like to talk about is going into some details of prompt engineering. And if we look at the traditional formulation of training a model versus a prompt formulation, we have the very big advantage of being able to use like a language model as is without doing any training. But we have the disadvantage that now we have a whole bunch of intermediate design decisions that tell us how, that determine how well our model is going to work, including what template we choose, what answers we choose, et cetera. So how do we define a suitable template? There's a bunch of different ways of doing this. And the first thing we need to do is define the shape. And then once we define the shape of the prompt, or like the total space of the prompts we will be considering, we have some way of kind of finding appropriate prompt templates. So as I mentioned before, a closed prompt, we fill in the slot. It looks a little bit like this. A prefix prompt, we have a slot at the end. And so once we've decided which one we want to use, which depends a lot on the task we're solving, the language model we're using, we'll want to design an appropriate template that allows us to achieve the task well. So the first way we can do this is with handcrafting, where we can manually choose a template based on our intuition or trial and error, other things like this. We can also do automated search, where we search either in a discrete space or search in a continuous space. And so I'm going to talk about a few representative methods for how we could do this search. So the first one is prompt mining. And the way prompt mining works is basically, given a small number of examples, we try to find examples that match the appropriate pattern for a prompt. So, sorry, given a small number of questions and answers, we want to find examples of prompts that match the form we want. So one thing that we could do is, like, let's say we have a list of, like 5 people. And their professions. So we have like Barack, well, let's do Joe Biden. Let's update my example. And president, what other good ones? This is the easiest question I'm going to ask you. Yes, you just need to tell me a person in the okay, Michael. It's actually a good example. Okay, any others? Don't make my life hard right away, okay?
Michael Jordan.
Michael. Okay. I'll do Elon Musk. CEO. So we have something like this, and what we do is we essentially extract templates that match that pattern. And so we'll find a whole bunch of text that says like Joe Biden serves as the president Joe Biden is the president, other things like this. And we can either extract all of the middle words that appeared between these templates, or we can do some sort of something that's more complicated, like we can calculate the syntactic structure or predict the syntactic structure of each of the sentences and extract based on the syntactic structure to get more complicated prompts. This is particularly useful for generating like close prompts, but you could use it for prefix prompts as well. And one caveat about this is you can generate, a bunch of noisy prompts as well, because like, for example, Joe Biden is a president, is the president, is not very informative, right? That could indicate a whole bunch of other, tasks other than the task of identifying somebody's profession, which is the one we want to solve. If you want to go deeper in this, there's a huge literature on this in like relation extraction and other things like this. There's bootstrapping methods to filter out noise in things, but I'm not going to go into that today. So another thing is prompt paraphrasing. And so this is where if you have an existing prompt, you can paraphrase it to get other candidates for prompts that you could be using. And some of these might be more appropriate or more useful. And this is, I think, particularly useful when you're doing manual prompt design, because it's very easy for somebody to come up with a prompt that's indicative of a, of the task that you want to solve, but it's not necessarily easy for a user, especially like a non-NLP, familiar user, to get in the head of the language model and figure out like which thing the language model would like the best. Like I've kind of developed my skills at doing this. Like, what I do is I think of, Joe Biden president, and what is the thing that hits the sweet spot of being like frequent but indicative of the task, but that's not necessarily easy for everybody to do. So you can generate a whole bunch of these things and use them. Any questions about these? Yeah.
How do you particularly remove biases from the training data in this case? Because if I were to say, US shares the border with, most probably it will come up with Mexico and not with Canada.
So the question was, how can we avoid biases in this process? And the example being, like, if we have the US shares a border with, it might say Mexico instead of Canada. Number one, be nice to our Canadian friends. Number two, I mean, this is obviously the case for, like a big country that shares a lot of borders, and it's going to be less likely to come up with other things. I don't know if there's actually, I don't know if that's a problem of our prompt design. I think there are issues with, there may be issues with prompts, but I think it's actually a bigger problem with the language model itself, right? Like if the language model is very biased towards high frequency things. And in fact, if we're talking only about predicting facts, it actually is a huge problem, because the model, like whenever it doesn't know where somebody was born, it predicts like US or France or, some major country. And there's actually a really interesting paper. I forget the name of the paper, but I think it's by Timo Schick. Actually, I hope I'm getting his name right. But there's a paper where and I also hope it's by him, but there's a paper where they demonstrate that like if you do this factual knowledge, it's actually overfitting on just the person's name. So like, for example, my name is Graham Neubig. My last name is very German. And if you put it into Bert, yeah, I haven't put it on the screen yet. So let's see if I can, so we have mass language modeling. So Germany, Berlin, Munich, Hamburg, and London. So
Where are you actually from?
I was born in Michigan. Yeah, so
A lot of Germans are looking.
there's a lot of Germans in Michigan. So Bob is right. It might predict Michigan more likely than the other ones, but you can see it basically, and then let me write Jordan, London. So you can see it's overfitting basically just based on the last name. It doesn't have any knowledge about where like I as an entity was actually born. So yeah, anyway, interesting question. So then moving on, there's other methods for prompt design. This is an automatic method for coming up with prompts and actually answers that allow you to predict the output appropriately. And the way it does it is it basically does a gradient-based search method where you treat the parameters of the prompt as parameters of the model that you want to be optimizing through like stochastic gradient descent. And so in order to do that, you have like a real joy as your original input, and then you have the trigger tokens, which are what I was calling the prompt template D4. And then you have the answer, which is the mask part. And basically you treat all of the pink parameters of the trigger tokens as things that you optimize through SGD. And so you find the optimal one, and then you kind of lock it into the parameters of an actual token. And one interesting thing here is that this can outperform on in-domain data sets, both of the methods that I talked about before, like prompt mining and prompt paraphrasing. However, the issue is that it gives you prompts that look a little bit like atmosphere dialogue cloned totally, which is not a very natural way to describe, like sentiment analysis, for example. So we're getting into the area where essentially it's no longer like actual natural language comprehensible text. So then if you go even a little bit further, you say, well, if this text is no longer text that we care about, if this is no longer text that we care about, then why don't we just directly optimize these parameters? And so you don't even care about these corresponding to an original vocabulary item. You can just make them be like trigger 1, like a special token like trigger 1, trigger 2, trigger 3. And you directly optimize these parameters here. And so now it's not even human readable anymore, it's just parameters of the model, but you get better results. This is traditionally called this is a method called prompt tuning. So prompt tuning, basically what it does is it appends these embeddings to the very beginning of the model. It appends these embeddings to the very beginning of the sequence and then runs them through the transformer. There's also another method called prefix tuning, which is, it's kind of complicated that we have two methods that sound very, very similar. But prefix tuning is doing essentially the same thing, except instead of only tuning the embedding parameters, it's tuning a prefix that you append to every layer of the model. So basically every So prompt tuning, basically, we have the frozen transformer parameters, and then we're only tuning the parameters of this prompt here. Whereas in prefix tuning, we're actually tuning something that we append to every layer. So it's important to know the difference between these two if you want to use them for something. And so there's actually kind of an interesting, expanding concentric circles here. So we have like human designed prompts. And then we have natural language prompts. So this would be like through prompt paraphrasing or prompt mining or something like this, because they're still comprehensible to humans. Then we have a discrete prompt. We have something like prompt tuning. Tuning. And then we have prefix tuning, which is like wider. So I'll put that up there because I'll get back to it in a second. So I think that's it's kind of interesting to think about. Or actually, maybe I'll just get back to this now. So one other point that I would like to make is so we have a paper that I talked about briefly before. So I talked about this paper before, towards a unified view of parameter efficient transfer learning. And what this paper basically shows is that prefix tuning is also a subset of a broader set of parameter efficient tuning methods. And so this includes other things like adapters and the stuff that I talked about before last class. And so one of the interesting things about this is that we can essentially go out gradually and get more and more general. So we can go with the human design prompts that people are using, natural language prompts, discrete prompt tuning, prefix tuning, parameter efficient tuning, and then just kind of like model fine tuning. Like maybe not just parameter efficient tuning, but you know, fine tuning in general. So it's kind of a way we can go gradually and make our training more and more general, more and more powerful. But at the same time, you start requiring like more training data, or you can't necessarily use the pre-trained model as is. So yeah. Cool. Any questions about that? Okay. So anytime somebody tells you like prompt tuning is hacky or something like, or sorry, prompt engineering is hacky, or you shouldn't be spending your time engineering all these prompts, you can tell them, but I'm way more parameter efficient than whatever you're doing. So, okay, great. So next I want to go to answer engineering. And answer engineering is kind of identifying the answers that you are going to be associating with labels. And so we have reformulated the task, so we should also reformulate our ground truth labels. So we have like fantastic being mapped to positive here. And so what we can think about is we can think about our answer space, and we can think about our label space. And generally what we want, it's not guaranteed that we need this, but generally what we want is we want a many to one mapping where we can have many things in the answer space, but we would only have one thing in the label space. Another way you could think about this is you could think of it as your probability over your potential answers, and a probability over your labels. And then you have a matrix here that maps the answers to the labels. So if you do this matrix multiply, you could take in the probabilities of the answers and output the labels, probability of the labels. And so actually, it doesn't necessarily need to be a many-to-one mapping. You could have it be a many-to-many mapping. Like you could say, this answer is indicative of positive, but it could also map to negative in some of the cases. So you could expand this to be more flexible if you wanted to. So then another question is, how do you search for an appropriate answer space and map it to the original output to result in an effective predictive model? And there's a number of different ways to do this. And again, we need to define the shape of the answer, and we need to decide how to search for appropriate answers. In some cases, you'll want your answer to be a token. This is particularly useful for like classification tasks or other things like this, where we can easily define the answers as tokens. It can also be a chunk. So a chunk of words made up of more than one token. And it can also be like a sentence or just continuation. And this can be used with a sentence of an arbitrary length. I say for the chunks, can usually be used with close prompts. I guess this could be used with either, but usually with close prompts. And then for sentences, this is usually used with prefix prompts, where we just generate the continuation. So here are some answers of things that you could be using for different, or some examples of answers that you could be using for different tasks. So for example, sentiments classification, you could be using tokens here. For topics, you could be using like tokens or spans. As you get down to things like text generation, then obviously for text generation, it makes more sense to just have it be freeform text and create the output. So in the case of text generation, the answer is equal to like in text generation, most of the time the answer will be like equal to the output modulo any like post-processing or things like this. But for a lot of other tasks, you have a label set like classification. You have a label set already decided, so you need to search for answers. So one way you can do that is with handcrafting. Another way you can do that is with automated search. And so for automated search, one way you can do that is you can start with an initial handcrafted set of answers and paraphrase them to expand the answer space. Another thing that you can do is you can define the answer space with several plausible answers, and then use an algorithm to further search over this prune space to select the final set of answers. Another thing, I don't think this is quite as common, but you can also decompose like multi-word tokens into single words, and then use the individual single words to make predictions as well. I'm not going to go into a lot of detail here in the interest of time. I only have 15 minutes left, but we have much more detail in the survey paper. So continuous search spaces, the simplest idea is you assign a virtual token for each class label and optimize the token embedding for each label. This is very simple. Basically, you just redefine the softmax matrix. You might like seed it with some reasonable inputs, or you might take like the average of several reasonable tokens, but then you can fine tune afterwards. And obviously, to do any of these search-based methods, you need at least a little bit of training data to pick the best result here. Okay, so some final, a few final advanced topics that nonetheless can be quite useful. So I'm going to talk a little bit about multi-prompt methods, and multi-prompt methods include things like this. So prompt ensembling, prompt augmentation, prompt composition, etc. So prompt ensembling is a very simple idea that we don't necessarily have the best prompt all of the time. A single prompt isn't always going to give us the best answer. And so we basically use multiple prompt templates to make predictions. And so we might come up with prompt number one, which is like X is capital is Z, Z is the capital of X, the capital of X is Z. And we combine together the predictions. Usually we'll combine together the predictions just using something like linear interpolation. So we have like, we have prompt I. We have the probability of Z given prompt I. And we just sum over them with some sort of mixture rate here. So this utilizes the complementary advantages of all of these prompts. It can also alleviate the cost of prompt engineering. And the reason why is because now you don't need to find one good one. You can just find a bunch of them, and hopefully together they will give you better results. So this is the weighted averaging that I talked about here. Sorry, I forgot I had this slide, but you can do uniform averaging where you just average them all together. You can do weighted averaging, majority voting, etc. So another thing which we called prompt augmentation in our survey, we thought this was maybe a clearer name, but actually now most people have called this in context learning. So I think I should probably change the title of the slide. But in context learning or prompt augmentation is basically where you add a few examples before you actually do the tasks. So it's you know, if you know that you want to be adding 6 and 8 together, and you have your input is 6 plus 8 equals blank, you'll add 1 plus 1 equals 2. That's 2 plus 5 equals 9. This is the second time I presented these slides, and I like second or third time I presented these slides, and that's the first time I've noticed that problem there.
For large values too.
Yeah. But anyway, so you can have multiple correct examples, and this basically helps models learn better. I think we're probably going to have a talk that talks about this in more detail later, and some of the theoretical reasons why this is a good idea. And one thing that you need to be careful about is that you need to be picking the right answers here. Like a good step would be not picking incorrect examples, but also there have been some papers. There's a nicely named paper, Fantastically Ordered Prompts and Where to Find Them. And basically what it shows is like just changing the order of the examples that you present actually has a big effect on the downstream accuracy of the model. Like if in tasks where the underlying accuracy is not perfect. Another interesting development that I didn't add to the slides, but I think is worth talking about is there's some interesting examples where basically if you want to start handling more complex tasks that require things like reasoning, it says this idea of chain of thought prompting, basically what it does is instead of taking a question and giving the answer directly, it takes the question and then it adds kind of the reasoning process that the model went through in order to get the answer. And it adds these to the in-context examples, and then you add another question, and then the model itself will kind of like quote unquote go through this reasoning process as it generates text. So a few people have asked me why I think this works, and this is my hypothesis. I don't know if I have very good evidence of this, but maybe some papers have demonstrated this. But basically, in order to do this right, in order to do this correctly here, you would essentially need to do all the necessary calculations within, one or a few passes through the transformer model's parameters, right? And, your transformer model is only, 175 billion parameters and, 16 layers deep or something like that. Despite the fact that your calculator could probably do this, once you put it in there, transformer models aren't like specialized for doing this. They're specialized for generating text, right? Or at least the ones that we trained to generate text. And so basically what I think this allows you to do is it allows you to do a bunch of simpler intermediate steps that, are more likely to succeed. And as long as all the simple intermediate steps succeed, which, they probably have a higher probability of doing because, they're simpler, that allows you to basically build upon these and eventually, come up to the answer. Another thing is a lot of math word problems like this exist on the web. And so basically, this is probably a more common pattern, possibly a more common pattern than, just having this without the answer. So, yeah.
So my intuition would be that if you did this with really big integers, it wouldn't be able to do it because there's not examples of those numbers.
If you did this with really big integers, it wouldn't be able to do it. So there's some interesting results where like very large models are able to do, multi-digit addition. But as I said, that's kind of like using, it's kind of like using a lot of GPU power to solve a problem that a calculator could solve. But
It's just a question of what it can do.
Yeah. But yeah, definitely like the larger the numbers get, the more likely it is to fail. Yeah, sorry, go ahead.
Is this a closed prompt based mechanism or
This is a prefix prompt here because you'll notice that it's all of the prompt happens before the actual output it's generating. And that's kind of important because it needs to generate a long sequence here explaining the quote unquote reasoning. Yeah. So another even more amazing paper. I love this paper because it totally doesn't make sense that it works until you think about it. So it's this paper. And basically what they show is you don't even need to provide examples of reasoning. What you need to do is you need to just write, let's think step by step at the beginning of the answer. And suddenly it starts working. And so why is this? I think the answer is similar, right? There's a bunch of these word problems somewhere online. So you basically, if you think about this, this is not a calculation model. This is a language model, right? So it's mimicking the language that it's seen before online. And so if there's lots of language that basically follows, let's think step by step with, these sorts of solutions, then that gets the model in the appropriate space, in the appropriate space of giving a solution like this. So yeah, I love the simpleness of this paper and the fact that it actually works. Cool. Okay. It also shows how a little bit of creativity can do wonders in this area, which is very rapidly developing, but we still don't know everything about it. Okay. So I also want to talk about prompt-based training strategies. You can look at them from the data perspective and the parameter perspective, how many parameters are updated, et cetera. So as I mentioned before, zero-shot learning, few-shot learning, full data learning is basically zero-shot is where we try to solve a problem without having any examples. Few-shot learning is where we have a few training examples, usually not enough training examples to do a good job if we just trained fully supervised. And full data is when we have lots of training examples, or maybe enough to do pretty well fully supervised. And so we have a breakdown here, which is also broken down in the survey paper that I cited. But basically, promptless fine-tuning is where we don't have any prompts, but we train all of the language model parameters. Tuning-free prompting is where we don't train any parameters. Another way to think about it would be the human-designed prompts in the middle here. Fixed LM prompt tuning is where we tune only the prompts parameters. So that would be up to maybe prefix tuning or maybe prompt tuning here. And fixed prompt LM tuning, this is not super widely used, but there's a nice example of it called PET, which basically takes a prompt and then fine-tunes the parameters of the LM to do better. And the reason why you might want to do this is because the prompt, essentially you can view it as a prior over what task the model should be solving after you train the parameters of the model. And so it's a better way to utilize the fact that the model already kind of knows to solve the task before you start tuning the model. And then PETA is an example where you basically add a prompt, but then you train everything. And so, you know, I think one interesting thing is these methods down here, given that creating a prompt for your task is not that hard, you know, you think for 15 minutes and you can come up with a pretty reasonable prompt. Adding a prompt to even full fine-tuning of your model seems like a not too bad idea. So if you, for example, have a homework that's due soon, there's an idea. It might not take too long, right? You just add something to the beginning of all of your sentences. Okay, so there's lots of different choices. There's too many, and it can be difficult to select. I'm sorry, I had an animation on this slide. It looked a lot better with the animation. But if you have a huge pre-trained model, you might just fix the LM, or if you have few training examples. If you have lots of training samples, you should definitely consider something where you're training at least some part of the parameters of the model. How many you train depends on how many examples you have, but that's a good thing to know as well. And I'd like to, yeah, maybe I'll just wrap up. So yeah, are there any questions before we finish?